Hello, everyone. Welcome to a new lecture of our course on heterogeneous systems. Today, we continue talking about GPU programming, and we are going to start focusing on important considerations for performance and optimizations of our codes. We already know the basics of GPU programming. In the first two lectures of GPU programming, we have covered the basics of the software hierarchy with the threads, blocks, and grid of threads that run the kernel, that execute the kernel that runs on the GPU. And we have also explained the memory hierarchy from the software and the hardware perspective. Remember that in the traditional program structure, we are going to execute sequential or modestly parallel sections of our code on the CPU, continue using serial code running on the CPU, and then at some point we will reach to sections of the code that are massively parallel. In those cases, we will execute a kernel on the GPU. Remember that when we launch a kernel on the GPU, this is executed by a grid of threads, and the grid of threads is organized into thread blocks, all of them with the same size, with the same number of threads. And these thread blocks are scheduled onto the GPU cores, onto the hardware. After the kernel termination, we have all thread blocks synchronizing. We can call this a coarse grain synchronization. Then some more serial code will run, or modestly parallel code will run on the host CPU, and at some point we will launch a new kernel. Remember as well that from the point of view of the memory hierarchy, from the point of view of the software, threads can access automatic variables that usually reside in GPU registers, and threads belonging to the same thread block can share data and can communicate through the scratchpad or shared memory. All threads and all thread blocks belonging to the same grid can access the same memory space in global memory and in constant memory. And these are also accessible by the host that will perform data transfers from the main memory of the host or the CPU to the global memory of the GPU to transfer the input arrays that the GPU kernels will have to use. And then the host as well can retrieve the results that the GPU threads, the GPU kernel produce in the global memory, and the host can transfer them to the main memory. Remember as well that we were talking about one of our first programming examples was matrix multiplication, and we talked also about how matrix multiplication can be optimized by using a tile implementation. With this tile implementation, we can take advantage of caches in CPUs typically, or a scratchpad like the shared memory or the register file in the GPUs. Essentially, the key idea when computing a tile implementation of matrix multiplication is to load tiles of the input matrices, in this case A and B, load these tiles into the cache or the scratchpad or the register file iteratively, performing multiplications of these submatrices, accumulating the partial results, and after having done so, go to the next tiles, in this case, these darker ones that you can see on the slide, go to the next tiles, load them into the cache or the shared memory, and continue with the computation. And here you can see the CUDA code for this tile matrix multiplication, where the first thing that we do is declaring the arrays in shared memory. Here we use these two variables, row and column, to identify what's the row and column of the element of the matrix, the output matrix that is assigned to each thread inside our GPU. And then in this for loop, we go several times on it in order to load all the tiles of the input matrices A and B into the shared memory, and then perform the computation. Observe how in these two first lines here, we are loading a particular tile of matrix A and a particular tile of matrix B into the space that we have previously allocated in shared memory. We need to synchronize the threads belonging to the same block in order to make sure that the data that will be used next is already in the shared memory. That data that has been loaded by threads belonging to different warps is already in shared memory. And then we go to the computation itself, where we perform this matrix multiplication of the submatrices that are already allocated, are already stored in the shared memory. After we are done with this computation, we need to synchronize again in order to not overwrite data in shared memory that might be needed by other threads that are still executing this for loop. Okay, let's talk about the main topic of today's lecture, performance considerations. In the end, what we are trying to do today is just enumerating what are important performance considerations for GPU programming and for code optimization. We are not going to go today into many, let's say, detailed examples of these different performance considerations. It's more like enumerating what are these different performance considerations, because we will elaborate on them in later lectures. In later lectures, we are going to talk about different parallel patterns, how to implement them efficiently on the GPU, and at the same time, we will be coming back to all these performance considerations and explaining how we have to write our code in order to optimize by taking all these considerations into account. So what are the main bottlenecks of GPU computing? Because we know that GPUs are extremely powerful devices, but still they suffer from the typical drawbacks or bottlenecks of the processor-centric systems. And the reason for that is that the data resides far from the CUDA cores, from the GPU cores. The data might reside either on the host memory or on the global memory of the GPU. In the first case, we need to transfer data from the main memory to the global memory of the GPU, and that's usually something that is going to take quite a bit of time, especially in GPUs that are discrete and need to perform the transfer over, for example, a PCI Express bus. It's true that these data transfers between the CPU and the GPU will be amortized at some point if we perform enough computation on the GPU and we reuse the data that was moved to the GPU memory. But then inside the GPU itself, when we are executing a GPU kernel, we have to access the data that was allocated in the global memory. And that's also going to be quite costly compared to the execution, the computation on the GPU cores. That's these global memory accesses, even though GPUs these days have higher and higher memory bandwidth, still this memory bandwidth is far from the large compute throughput that the GPU cores can provide. So that's why today, most of the time, we will be talking about how we access the global memory or how we transfer data between the CPU memory and the GPU memory. We are going to start with the access to the global memory and what are the important considerations when we access global memory and we want to do it in an efficient way. And one of the first things to take into account is that GPUs are multi-threaded architectures and they have the ability to hide long latency operations by executing other operations. And one of these long latency operations, if not the most, let's say, important to take into account is the access to the global memory, because these are very long latency operations. In order to be able to hide these latencies, it's important that we have enough warps executing on the GPU cores, because these warps that are executing on the GPU in the GPU cores will be the ones that will be running, executing arithmetic operations in the GPU pipeline, while other warps need to go to the global memory to bring data. And in order to be efficient in this latency hiding mechanism, we need to have enough warps in the GPU pipeline. And that is given by a metric called the occupancy, as we will see. In the access to global memory, it's also important to take advantage as much as possible of the cache lines that we bring from the global memory. And that's essentially what we call coalescing the memory accesses. We will see what is a coalesced memory access, and we will see how we can achieve a coalesced memory access in order to maximize the memory bandwidth. And then, and this is something that we already introduced in the previous lecture, we will have to take advantage of the data reuse that exists in the GPU kernels. The other day, we already started to explain how to use memory, the shared memory, in order to take advantage of this data reuse. We are going to talk a little bit more about that today, but also we will talk about important considerations to take into account when we access the shared memory, because it's a bank memory, and same as in any other bank memory, we can suffer bank conflicts, and these bank conflicts will make the accesses longer and will reduce the sustained bandwidth of access to the shared memory. Then it comes the execution inside the GPU cores themselves. Remember that GPU cores are SIMD engines, and because they are SIMD engines, the best way of taking advantage of their compute power is by having all threads running on all lanes of the SIMD units executing exactly the same code. This way, we avoid the divergence. This way, we don't need to worry about mask execution. We don't need to worry about branch divergence, and we take more advantage of the underlying hardware. We are going to start introducing how to optimize SIMD utilization in GPU programs, and we will continue as well in later lectures, because this is an important performance consideration. And then there are other considerations that we are also going to briefly introduce today, but we will elaborate more in later lectures. The first one of them is the use of atomic operations that are read, modify, write operations that happen atomically, and they are extremely useful to avoid data races, but they also have the problem that they cause serialization, because if you have two threads running at the same time, for example, in the same warp, and they want to go to memory and update the same value in memory in an atomic manner, they will need to serialize. And when they have to serialize, what that means is that we are reducing the utilization of our SIMD units, and consequently, we are harming the performance. And finally, the data transfer between CPU and GPU that I mentioned in the beginning. There are ways of trying to deal with the cost of these data transfers. There are ways to trying to overlap the communication, these data transfers, with the computation that happens inside the GPU, and we are going to start talking about how to do that today. Okay, so let's start with from the beginning. Let's start from the access to memory. When we talk about memory, it might be the global memory, or it might be the shared memory. The access to global memory is extremely important to try to optimize, because, as you know, it's far away from the GPU cores, and accessing data that resides in the global memory takes a few hundred of cycles. So that's why we start from there. But remember that the GPUs are multi-thread architectures, and because they are multi-thread architectures, they have the ability to tolerate long latency operations. And the most representative of these long latency operations are the accesses to the global memory that will have to happen every time that the threads running on these SIMD lanes here do not find data in either the cache or the shared memory, and they have to go to the global memory to bring data and continue the computation. And when we are doing so, we want to take advantage of the latency hiding mechanism that fine-grained multi-threading architectures provide. But this latency hiding mechanism depends and is only effective if we have enough threads or enough warps that are able to run computation on the GPU cores while we are performing the access to global memory for other cores. And the number or the ratio of warps that we have running on the GPU over the maximum possible number of warps that we could have on a GPU core is what we call the occupancy. And here you can see in this slide a very simplified, a very toy example of what's the impact of the occupancy. Imagine in this toy example that we have 4 active warps, and at some point in time we are executing instruction 3 for warp 0, and after that we launch instruction 2 for warp 1, and after that instruction 4 for warp 0. But it turns out that this instruction 4 is a long latency operation and access to global memory. At the same time, while we are waiting for instruction 4 to complete for this warp 0, we can continue the execution of instructions in the GPU core pipeline. For example, instruction 1 for warp 2, instruction 1 for warp 3, and so on, or instruction 3 for warp 1. Sometime later, the long latency operation will have finished, and then warp 0 can continue the execution, in this case with the next instruction, that is instruction 5. But as you can see, we could hide all these latency here from the access to global memory by executing instructions for other warps in the GPU pipeline. However, if your utilization is lower, for example, only 2 active warps, what may happen is that at some point we won't be able to schedule new warps, new instructions from other warps on the GPU pipeline, and we will have to wait until the long latency operation finishes. So we would be wasting execution resources during all this gap here. So that's why it's important to have an occupancy value that is high enough. It doesn't need to be 100% in all cases. We may be able to achieve this latency hiding with lower occupancy values, but in the end, it's like a good reference of what's going to be the performance of a program. Occupancy depends on the usage of the SM or GPU core resources. And just to give you a few numbers, a few typical values here, like the maximum number of warps that we can run on an SM or a GPU core in current architectures is around 64 warps, which means 2048 threads. The maximum number of blocks per SM, there is also a limited number of maximum number of blocks that can run on a GPU core is around 32 in current architectures. The register usage, because we have large register files, and these register files, as you know, are partitioned, and registers they are assigned to the threads that run on the GPU core. These are pretty large, but in the end is also not an infinite resource, same as the shared memory. And here you can see, like, say, typical values in modern GPU architectures. How do we calculate the occupancy? We have to take these resources into consideration, and we also have to take into account what are the number of threads that we are launching in each block. Remember that each block maps to one GPU core, and that's going to help us define what's the occupancy of a kernel. So to calculate the occupancy, we should know what's the number of threads per block. That is something that programmers define. We need to know what's the number of registers per thread. That depends on the automatic variables that we have in our code, and it depends on our code itself, how it's written. And this is something that we can know at compile time, because the compiler allocates the registers to the threads. So the compiler can give us this information of how many registers each thread is going to need, and also finally the shared memory per block that is also defined by the programmer, because we as programmers have to allocate this shared memory, and we can reserve as much as we need. We could let's say perform the calculation of the occupancy manually, but over the years we have been using a very useful tool, an Excel sheet that is called the CUDA occupancy calculator. As you can see here, it's parameterizable depending on what's the compute capability, or what's the GPU architecture. In this case, in this screenshot, you see that numbers here are for the compute capability 8.6, that corresponds to the Ampere architecture. This Ampere architecture has, in this particular case, 64 kilobytes of shared memory. And here in this orange area, we enter what's the number of threads per block that we are using, that we are going to launch in our program in the execution configuration. What's the number of registers per thread? As I said, this is something that we can know from the compiler after the compiler allocates the registers, and what's the usage of shared memory per block. And based on these numbers here, and based on the resources that the actual architecture have, we will obtain the occupancy of each multiprocessor. In this particular example, we achieve 100% occupancy. If we change slightly some of these numbers, like for example, the thread per blocks, we see how the actual value of the occupancy might change. So if we go, for example, from 256 to 320 threads per block, the occupancy decreases a little bit in this case, but we can again go to an upper value if we use 384 threads per block. And as you see also how the occupancy depends on the registers per thread. The more registers we use, the lower the overall occupancy will be. And same here for the shared memory. You can access the CUDA occupancy calculator from the CUDA programming guide. It's downloadable from here. However, as you can see on the slide, this CUDA occupancy calculator is now deprecated in the most recent version of the CUDA programming guide. What the CUDA programming guide now recommends is that we use the occupancy calculator that comes with NVIDIA Insight, which is one of the profilers that CUDA provides. And it's probably even easier tool to use than the Excel sheet. Okay, so now we know how GPUs hide long latency operations like accesses to global memory. We know how important it is to have enough threads running and enough warps running in each GPU core in order to be able to take advantage of this latency hiding mechanism. Now we are going to discuss how we have to access memory, how each warp needs to access memory in order to take advantage of the available bandwidth and in order to maximize the sustained bandwidth that we can obtain or we can achieve in our GPU programs. We are going to talk about that. Remember that in CUDA, we have the same memory layout as in C. Is matrices or two-dimensional matrices, for example, are typically stored in a row major layout, as you can see on the screen. So we are going to talk, for example, about how to access a two-dimensional organization like this. But first of all, let me recap a little bit and refresh a little bit on how DRAM, the DRAM subsystem works with a top-down view. And because understanding and refreshing how DRAM operates is going to be useful and important to better understand the performance considerations that relate to the access to the global memory. So how is the DRAM subsystem organized? It's in this top-down organization. We can start from the memory channels that are actually the channels that connect the CPU processor, the CPU or the processor or the GPU to the memory itself. The memory itself is going to be composed typically by DIMMs, but by memory modules. Inside these memory modules, we have one or two ranks. Typically, these ranks are composed by memory chips, and inside the memory chips, we have memory banks. And then the banks are like two-dimensional organizations of memory cells, of DRAM cells, and are organized into rows and columns. So let's go one by one. Let's go step by step, reviewing all these levels of the DRAM system organization. First one are the memory channels, as I said, connect the processor or the CPU or the GPU with the memory DIMMs, and these memory channels are accessible from the memory controllers of the processors. Each memory controller can handle one memory channel or maybe more than one memory channel. And then connected to each memory channel, we may have one DIMM or maybe several DIMMs. As you can see in this slide, we have like two DIMMs per memory channel. If we go closer to the DIMM, to this dual inline memory module, we see that it has two sides. And on these two sides, we normally have a few chips, right? Each of these sides corresponds to what we call a rank. In this specific example, rank 0 is a collection of 8 chips, same as rank 1. And if we take a closer look at the rank, we see that there are multiple chips, and in this particular example, there are 8 chips. And every time that we want to read for example, one cache line, or for example, one element from this memory, we would be accessing all these chips at the same time and bringing out some bits of the corresponding words or the corresponding cache lines. In this particular example, bits 0 to 7 are accessed in chip 0, bits 8 to 15 are accessed in chip 1, and so on and so forth. And if we go closer and take a look at the internals of one chip, we'll see that there are different banks. And these banks can be addressed by using certain bits of the memory address, but yeah, depending on these bits of the memory address, we would be accessing a different bank. But let's take a closer look at the banks. If we look at the internals of one bank, these banks are composed by several DRAM subarrays that are like 2D arrays of DRAM cells. In this slide, these blue dots represent DRAM cells. And as you see, these DRAM cells are connected by using horizontal word lines and vertical bit lines. As you see, at the end of these, or at the bottom of each bit line, we have sense amplifiers that are going to be used to amplify the values that we put in the bit line. And all these sense amplifiers together, these sense amplifiers in each subarray are what we call the local row buffer. We can take a closer look at each of the DRAM cells, and we see that each DRAM cell is composed by a storage capacitor and an access transistor. As you see, the access transistor is controlled by the word line, and this access transistor can provide the connection between the storage capacitor and the bit line for either read the data that resides in the capacitors or write data into them. Let's take a closer look at the DRAM cell operation. The DRAM cell operation consists of 3 main steps: activate, the second step is read or write, and the final step is pre-charge. Let's start from the beginning. Let's start from the activate operation. In this case, the memory controller will issue an activate command onto one DRAM bank, and in particular, one row of the bank, of one subarray in the bank. And what happens when the memory controller issues an activate operation, an activate command, is that first of all, we will rise the word line of the corresponding row, that row that wants to be accessed by the memory controller. When we rise the word line, we are closing this switch that represents the access transistor, and what that means is the capacitor. So the access transistor starts conducting, and the capacitor starts sharing its charge with the bit line. And what that happens is that so this causes a perturbation in the voltage of the bit line. In the beginning, the voltage of the bit line is half VDD, and after the capacitor starts sharing the charge with the bit line, this voltage here can go either a little bit up or a little bit down in the bit line. At that point, we will enable the sense amplifier. When we enable the sense amplifier, what the sense amplifier does is amplifying the voltage of the bit line. It amplifies this deviation in the bit line. So if the deviation was a little bit higher than half VDD, what happens here is that the bit line goes to VDD. However, if the perturbation was negative and the voltage of the bit line was below half VDD, then the amplification of the amplifier would cause that the bit line goes to 0 volts. In this specific example, it goes to VDD, as you can see. After this happens, and because the word line is raised, is set, the access transistor conducts, and that means that the charge of the capacitor is restored. And then the row buffer stores the cell value. So if we had 1 here, now we have 1 here in the sense amplifier. If we had zeros here in the storage capacitor, now we have 0 in the sense amplifier. And at this point, the sense amplifiers, the local row buffer contains the values that were or are stored in the specific DRAM row. And at that point, we can start reading the values, latch in the sense amplifiers, or we can write values into these sense amplifiers in order to later move these values back to the storage capacitors. And that's actually what can happen when we pre-charge, right? So in the pre-charge operation, we will first lower the word length. This makes that the voltage of the VDD of the bit line goes to half VDD. We pre-charge. That's what pre-charging means. Pre-charging the bit line for the next access, and then we disable the sense amplifier. So now we have a recap on how the specific DRAM cells operate. Now let's take a look at how the whole DRAM bank works when we want to read or write data from or to some specific DRAM rows. Remember that the bank and the subarrays in it are two-dimensional organizations of DRAM cells. So they are composed by multiple columns and multiple rows. As you know as well, these arrays, these subarrays are connected to the row buffer, to a local row buffer that in principle will be empty. And at some point, we want to perform an access. Let's assume that we are doing read accesses. And in this case, we want to access element 00, the element that resides or the cache line that resides in row 0 and column 0. In order to access these, we need to use our row decoder. The input to this row decoder is the address of the specific row. In this case, it's row 0, and this row decoder will write the word lines of the whole row where the data that we want to access resides. And after this row is activated, as you know, and as you have seen in the previous slides, the row is copied to the row buffer. At that point, we can use the column address to access the specific elements or specific cache lines inside this row 0 that we want to access. And we use the column address in that case. So that's the element in row 0 and column 0. So we read these out of the DRAM bank. Let's assume that our next access is to row 0 and column 1. And now observe that good thing is that the row 0 is already in the row buffer. So we don't have to go again to the row decoder and open a new row. However, we can directly read this column address 1 from row 0 because the row 0 is already in the row buffer, and we have what we call a row buffer hit. So next, we want to access column 85 in row 0, and again, we have a row hit. And by using or by activating column address 85, we read the corresponding element. But observe that our next access is now to row 1. So that means that we cannot use anymore row 0 that is already stored in the row buffer. We have what we call a row buffer conflict. So what we have to do is closing this row 0, pre-charging the bit line, and then activating a new row, in this case, row with address equal to 1. We activate this row, we move this row to the row buffer, and now we can access, in this case, column 0 of row 1. So observe that in the end, there is a different latency for different accesses to the DRAM bank. If the row is already open and we have a row buffer hit, we will have a much faster access than if we have a row conflict, because that entails that we need to close a row, we need to open a new row, bring it to the row buffer, and then start accessing the desired columns. So this is important for us to introduce the concept of DRAM bars. In the end, you can identify one DRAM bars with one DRAM row. And we have just seen this example where we want to access data in consecutive accesses to the memory, we want to access data that resides in different parts or in different rows. What that means is that we will have to wait a certain latency, let's say a few tens of nanoseconds before the row is already available in the local row buffer. And at that point, we can access the column that we want to access. But after that, if we have a row conflict and we have to close the row and open a new row, we'll have to wait again for all this long latency until we can access the next element that we wanted to access or the next cache line. When we access data from the same bars or the same row, things can be much faster, can be much lower latency, because after having paid the long latency of opening a new row, we can access several elements or several cache lines one after the other, as you see, and we are saving a large amount of time in comparison to the other case where we have consecutive accesses to different bars or different rows. So accessing data in the same bars is faster than accessing data in different bars. There are more things to consider when we access memory. Is the fact that memory is composed by multiple banks, as we have seen a few slides ago, and as we also discussed the day that we presented the SIMD and GPU architectures. Remember that when we want to sustain multiple accesses at the same time, which is something that makes sense in GPUs and SIMD processors, because we have multiple threads, or we are operating on multiple data elements at the same time, it makes sense for us to be able to sustain multiple memory accesses at the same time. And the way of doing so is by dividing the memory into multiple banks that can be accessed concurrently. Remember, we explained this in the corresponding lecture, SIMD processors and GPUs. Remember that in order to perform, let's say, n accesses to this bank memory, what we would do first is, in one cycle, we place the desired address here in this memory address register. In the next cycle, we do the same for bank 1. In the next cycle, we do the same for bank 2. And after a few cycles, after having completed the latency that we need to bring the data, to fetch the data from a specific bank out to the data bus, we would have the data in this MDR, memory data register, and ready to move it to the processor, to the CPU, or to the GPU by using this data bus. One cycle later, we will have the result, the value read from bank 1, one cycle later from bank 2, and so on. So banks are useful to take advantage of memories and make better use of the available bandwidth and exploit more bandwidth. Channels are essentially the same. We can have multiple channels. Remember that connected to these channels, we have multiple beams, and we perform accesses to all these channels in parallel. So we can talk about bank level parallelism, and same as we can talk about channel level parallelism. So multiple banks, as we know, enable concurrent DRAM access, and bits in the address determine which bank an address resides in. And regarding the channels, is essentially the same, but it's even better, because when we have multiple channels, we also have multiple databases, and that means increased bandwidth. However, these ideas of enabling more concurrency by using more banks or using channels we also have to be careful, because we may end up happening bank conflicts or channel conflicts. What happens when we have a conflict? What would happen is that we will have to wait until the previous accesses to the same bank or to the same channel have completed before we can start a new access. However, there are ways of dealing with this. One way is, for example, changing the data layout that we have in memory in order to reduce the potential conflicts and be able to access more data concurrently. And there are also other ways, like, for example, using low order bits that have normally more entropy. So what that means is that the accesses are going to be more scattered, and this way we can expect that lower amount of conflicts. And also there are solutions that randomize the accesses to the memories by using hash functions. These hash functions, for example, can be implemented by XORing different bits of the address. So when we have multiple banks, we can better hide the latency because we can, let's say, read values, read data from different banks while we are paying the latency of opening rows in different banks. So if we have a single bank, we have to wait long latency until we open one row, then we access several columns in this row, then we have to open another row, and then we access several columns in that row. But observe that all these, let's say, lighter green here means a long latency that we have to wait before we are actually able to access data from memory. If we have multiple banks inside the same channel, what we can do is performing accesses to other banks while we are opening new rows in the previous banks, as you can see. So we will take full advantage of this possibility of having multiple banks when we have multiple threads accessing memory. And that happens when the occupancy in the GPU cores or DSMs is large enough. So after having reviewed this DRAM memory subsystem and this top-down approach, we are going to go into more specific details about how we have to access memory in GPUs. But if you want to learn more about the memory organization and technology, I can recommend you this lecture from Professor Mutlu delivered in spring 2021. But now let's talk about memory coalescing and what we mean by memory coalescing. We say that when threads in the same warp access consecutive memory locations in the same bars, the accesses can be combined and served in one burst. In this case, only one DRAM transaction is needed, and this is what we call the memory coalescing. However, if threads in the same warp access locations that are not in the same burst, the accesses cannot be combined. So multiple transactions are needed, and this will make that it takes longer to serve the warp, to serve the data that the warp needs. And that's what we call memory uncoalescing or memory divergence. Notice the difference here. If we go to memory, we have, let's say, one whole warp, all 32 threads of the warp want to read data from the memory, and we go to memory, we open one row, we place this row in the local row buffer, and we start reading elements or reading cache lines from this local row buffer. If all threads from the same warp that access memory all together, because they execute all together, because they are a SIMD unit, if these 32 threads want to get data that belongs to the same DRAM bars that is already in the local row buffer, the access will be much faster and much more efficient than if two threads or more threads belonging to the same warp need to access data that resides in different rows. Because if that happens, we will have row buffer conflicts, and that means that we'll have to close a row, open a new row, and again, pay all these long latency. So that's the difference between a coalesced access and an uncoalesced access. Let's take a closer look at this by discussing how these, the accesses to memory look like. So when accessing global memory, we want to make sure that concurrent threads access nearby memory locations. And that's the way of achieving peak bandwidth utilization, when threads belonging to the same warp access one single cache line or several consecutive cache lines. That depends on what's the size of the elements, the words that each thread in the warp wants to access, and also what's the size of the cache lines. But that's essentially the idea. We will maximize the bandwidth to the global memory if the threads that belong to the same warp access data that resides nearby. So this is going to see, you are going to see here an example of an uncoalesced or not coalesced memory access. Imagine that we have these two threads, thread 1 and thread 0. They are accessing elements in one matrix, in this case matrix MD, and now imagine that they are accessing the elements in this way. What that means is that the first access of thread 1 happens here, second access of thread 1 happens here, while the first access of thread 2 happens here, and the second access of thread 2 happens here. Now notice that for first access and second access of both, there is a long distance between the where these elements reside in memory. There is a long stride between the elements that thread 1 and thread 2 want to access. So these elements are not in the same cache line, or they are not in several consecutive cache lines. They are likely in different rows. So the access, different rows, so the access will be not coalesced. However, in this case, we have thread 1 accessing here, thread 2 accessing here, and the first element that thread 1 accesses resides here, while this first element that thread 2 accesses resides here. So this means that they are in nearby memory locations. They likely belong to the same cache line. And what that means is that in one single access, one single DRAM transaction, we can access the data that both threads need. And that's a coalesced memory access. Let's see a more detailed example. Let's say this is an example of uncoalesced memory accesses, where this is the access direction in kernel code. So we are going to assign different threads to these different rows. Thread 1 or thread 0 goes all over this row, yellow row. The next thread goes all over this red row, and so on. Because we know that this matrix has a linear row major layout in the memory. In the first cycle, or in the first access, this thread 1 accesses this element M00, thread 2 accesses this element M01, thread 3 accesses this element M02. And in the next cycle, we would have thread 1 accessing the next element in the yellow row, thread 2 accessing the next element in the red row, and so on. However, what's the problem here is that the distance between the elements that consecutive threads are accessing in the same cycle, in the same time period, is pretty long. And this long stride makes that they need to access data in different DRAM bursts. And that's why we have an uncoalesced memory access. However, we could distribute the computation in a way that the access direction in the kernel code is like that, is this as given by this vertical row. And what that would mean is that in the first time period, the 4 threads are accessing 4 consecutive elements belonging to row, the yellow row. And in the next time period, they access 4 consecutive elements in the red row. So observe that these threads are accessing elements that belong to the same cache line, or they are in nearby memory locations. In this case, the accesses to the global memory are coalesced, and we are taking full advantage of the available bandwidth. This ability of accessing memory in a coalesced or not coalesced manner is also important for the way that we store the data in memory. Imagine that we are using an array that contains tuples, and these tuples have 4 different values. In this case, 3 floating point values and 1 integer value, same as you can see here in the example. There are 2 different ways of organizing this in memory. There might be more, but let's say the 2 most simplest ways of organizing this array of tuples in memory is by either storing them as a structure of arrays or storing them as an array of structures. In the structure of arrays, what we have is a large array where that is divided in 4 parts. One of the parts, we have all the blue elements, all elements of A. Next, we have all the green elements. Next, we have all the yellow elements. And next, we have all the red elements. This is what we call the structure of arrays. The other possibility is to interleave elements from different colors. So as you see here, we have blue, green, yellow, red, blue, green, yellow, red. So each of them can be considered a struct, and the whole thing is an array of structures. Depending on the machine where we are using this array of structures or structure of arrays, we will have a more or less efficient access to the memory. Imagine that we have like a GPU, and inside the GPU we have multiple threads. These threads, by using the, we have written more code by using the SPMD programming model, single program, multiple data. So all threads are executing exactly the same code. These threads first need to access blue elements. If these threads need to access blue elements, thread 0 will access this element here, thread 1 will access this element here, thread 2 will access this element here. And at some point, they will go to the green values, and then they will go to the yellow values, and so on. Now, if these threads 0 to 2 belong to the same warp, notice that they are accessing 1, 2, 3 consecutive memory locations. And these consecutive memory locations will likely belong to the same DRAM bars, so we can achieve maximum bandwidth when accessing this structure of arrays. However, if we try to use an array of structures inside the GPU, in the first cycle, in the first access, we will have thread 0 here, thread 1 here, thread 2 here, and so on. And now notice that there is a stride between the accesses of nearby threads, of neighboring threads. This stride makes that the accesses will likely go to different DRAM bars, and this way we have uncoalesced accesses. We are not taking full advantage of the available memory bandwidth. However, if you think about a CPU, it might be the other way around, because the CPU will likely execute in a serial manner the whole computation for all these tuple here, and then the whole computation for all these tuple here, and then this tuple here, and so on. And what that means is that when the CPU thread accesses this element, the rest or the next elements are also coming to memory, are also coming closer to the core, to the cache, because they belong to the same cache line. And the good thing of that is that after having accessed the blue element or the blue value, the CPU thread needs to access the green and then the yellow and so on, and it will hit the cache because they belong to the same cache line. And here you can actually see what's the effect on the sustained bandwidth or the memory throughput that these different ways of accessing memories may have in GPUs and in CPUs. In particular, these experiments were run on an AMD Kaveri, that is an integrated system with a CPU and a GPU. By using the GPU, we measured the bandwidth for different strides. What that means is that accesses, consecutive accesses, or accesses of consecutive threads of neighboring threads would be done with a certain stride, with a certain distance, depending on what's the structure size. So if the stride is 1, as you see, we achieve the maximum bandwidth. If the stride is 2, the bandwidth essentially goes to half or even less. If it's 4, it continues going down. And at some point it saturates that its minimum bandwidth value. However, on the CPU, increasing the stride is not necessarily something bad, and as you see, it can take advantage of an array of a structure organization, and as you see, even increasing throughput as we increase the structure size. But not in all cases we would be able to perform coalesced accesses. That will depend on how we need to access the memory. And actually remember the example that we covered in our previous lecture, the matrix multiplication, and we said that one of the problems with matrix multiplication is that the access to matrix B, that is typically accessed by columns, would have in the, let's say, naive or most straightforward implementation, would have strided accesses to different cache lines, and then uncoalesced memory accesses. And that's what happened. Remember, in the example our previous lecture, they were matrices A and B. Here we call them matrix M and N. Matrix M is accessed by rows. However, matrix N is accessed by columns. And when that happens, when one thread needs to access the elements of the same column, what is happening is that they are going to different cache lines all the time. So one way of dealing with these uncoalesced accesses is by using the tile access pattern and take advantage of the scratchpad memory. After having copied the tiles into the scratchpad memory or the shared memory, we can perform the multiplication. And in this case, we just, let's say, go over the rows and the columns in shared memory where we have no problem with the memory coalescing in the same way as at least than we have when accessing the global memory. And shared memory, as you know, is also very useful to take advantage of data reuse. This is actually an example that we covered in our previous lecture, a Gaussian filter being applied onto an image. Remember that in order to compute each output pixel, what we are doing is the convolution of one filter that here is represented by this greenish window, and we perform the convolution of the filter and the elements that are the pixels that are under the filter. And if we compute the output pixel corresponding to this position, observe that we would be reusing some of the pixels that we needed for the computation of this pixel here. So there is data reuse, and the way of taking advantage of this data reuse is by using tiling or blocking, as we also call it in our previous lecture. That essentially means dividing, in this case, the input image into tiles, loading these tiles into the shared memory, and then computing by using the values that we have in shared memory. Shared memory is on chip, so the access is much faster, and we can certainly improve the performance of our program. However, shared memory is an interleaved or banked memory, and this might entail some issues, right? If we have bank conflicts, as we have discussed previously, and now we are going to see some examples. Typically, in NVIDIA GPUs, the shared memory has 32 banks, and typically the way that one specific element is mapped onto the banks is by applying this expression here. So address modulo 32 will give us the exact bank where a specific address resides. There will be bank conflicts whenever we have two threads belonging to the same warp that need to access data that resides in the same bank, because the warps access, all threads of the warp access at the same time. If these two threads belonging to the same warp need to go to the same bank, they'll have to wait, or one of them will have to wait until the other one is done. Let's first see an example of what is a bank conflict-free access. In this case, let's consider a bank of 16 banks with a linear addressing with the stride equal 1, where thread 0 accesses one element in bank 0, thread 1 accesses one element in bank 1, and so on. We have linear addressing, so there are no bank conflicts, even if the accesses are permuted or random in this case, but there are no two threads accessing values in the same bank. We are fine. We have a bank conflict-free access. However, we will have conflicts every time that we have threads accessing two threads or more threads accessing elements that reside in the same bank. For example, if the stride is 2, what that means is that thread 0 accesses bank 0, thread 1 accesses bank 2, thread 2 accesses bank 4, and at some point, thread 8 will access bank 0. So that's why we have a two-way bank conflict in these even-numbered banks. Or it might be even worse when we have more than 2 threads colliding in the same bank. In this particular example, we have an 8-way bank conflict in bank 0 and in bank 8. So we may have bank conflicts when we access shared memory, and that's actually something to take into account as well when we use tiles in shared memory. We need to find ways of reducing shared memory bank conflicts. We will discuss about some of these ways in later lectures, but for now, let me tell you, or let me remind you that bank conflicts are only possible within a warp. There are no bank conflicts between different warps. We can deal in different ways with the strided accesses, with some optimization techniques. These are some things that we will cover in later lectures. Padding is a way of dealing with strided accesses and avoiding bank conflicts, but we can also use randomized mappings as those that were proposed in this ISCA 1991 paper by Borprau, and more recently, we have proposed as well, along the same lines, some hash functions for scratchpad memories of GPUs, high XOR-based hash functions that definitely resulted in very good performance improvement in both software implementations and hardware implementations as well. Okay, now we have more or less covered the different performance considerations to take into account when we access global memory, when we access shared memory. As I said, we will continue discussing these important performance considerations in later lectures when we talk about specific examples of specific parallel patterns. Now we go to the next of our performance considerations, is the SIMD utilization. Remember that GPUs are SIMD machines. SIMD machines are best utilized when we take advantage of all the SIMD lanes that a SIMD unit can take advantage of. And what that means is that we don't underutilize our resources by just leaving some lanes unused. But still, this is something that may happen. And if you remember from our lecture where we talk about the architecture of SIMD processors and GPUs, it will be possible for threads being programmed by using the single program multiple data programming model. It's possible for these threads to diverge even if they belong to the same warp. That's what we call the intra-warp divergence or branch divergence as well. Notice how all these threads that are from the same warp in reality cannot execute all together because some of them go through path A while others go through path B. Remember as well that it was possible to handle these by using masks, by using what we call the conditional or predicated execution, but that's, even though it's functional, is not desirable because it affects the actual performance. Here you can see another example. This is an example of intra-warp divergence. In this particular case, we want even threads do these and odd threads or odd number threads to do that. What that means is that these even and odd number threads are serializing and then executing the odd numbered ones only after the even numbered ones finished. So here we have divergence, and as you see, we take twice the amount of cycles to complete the whole execution in some way. But there might be ways of optimizing as well the SIMD utilization if we play with the way that we access data. We can distribute the computation in a different way. In this specific example, what we are going to do is telling all these threads that have an index lower than 32 to do these and the remaining threads to do that. If we do that, in this case, the do this is being done by these threads here while they do that is being done by these threads here, and these threads are consecutive, so there is no divergence among them. These threads here are consecutive, so there's no divergence among them, and we will likely achieve higher performance with this divergence-free execution. These considerations, again, we are going to cover them with a lot of detailing an upcoming lecture about the parallel reduction. In order for you to start understanding how important is this, let me show you one example. What would be a naive mapping of a vector reduction? Remember that in a vector reduction, we have an input vector, and what we want to calculate is the reduced value of this vector. For example, the sum of all the elements of this vector. This is an operation that we typically do by using a tree-based approach that essentially means that in every iteration of the calculation, half of the threads retire while the remaining threads continue performing additions. For example, in the first iteration, we have thread 0 that is going to add these two elements, 0 and 1. Thread 2 is going to add these two elements, 2 and 3, and so on. In the next iteration, half of the threads retire, and they perform the subsequent additions. In this case, thread 0 is adding this partial sum here and this partial sum here, and storing them in certain position. And in the next iteration, again, half of the threads retire, and so on. The problem with this code is that it has a very low SIMD utilization. There is divergence. Why is that? Because observe how we are only using thread 0, 2, 4. However, we are not using thread 1, 3, 5, etc. These threads, odd number threads, also belong to the same warp, so we are not using them. We have intra-warp divergence, and the performance will be heavily affected. We are going to discuss much more in detail, as I said, in our upcoming lecture about the parallel reduction. However, in a divergence-free mapping, what we would do is assigning consecutive threads to the specific computation that we want to do. In this particular example, this thread 0 is adding elements 0 and 16. Thread 1 is adding elements 1 and 17, and so on. When threads start retiring, we have lower utilization for sure, because not all threads are going to be used, not all warps are going to be used. However, the threads that keep working are consecutive, so likely they belong to the same warp, and because they belong to the same warp, we have an execution with higher SIMD utilization. As I said, we will cover this in more detail in an upcoming lecture. Now it's time to talk about the other considerations. I mentioned as well in the beginning of the lecture, atomic operations. Atomic operations are extremely useful because they perform read, modify, and write operations atomically. CUDA provides atomic operations since almost the very beginning on shared memory and on global memory. There are different atomic operations, some of them executing arithmetic functions or bitwise operations as well. Here you can see one example. This is an atomic add. This is the pointer to the shared or global memory where the specific value that we want to update resides. This is the value to add in this particular case of the atomic add, and this is the return value, that is the old value that was stored in that position of shared memory or global memory. As I said, there are also bitwise operations and different data types. If you want to know what are the exact operations and the exact data types that atomic operations can handle, please go to the CUDA programming guide. Atomic operations are very useful because they allow different threads executing at the same time to avoid data races, and this way have, let's say, correct final results. The problem is that they may serialize the execution if these threads that need to access and update the same elements in memory belong, for example, to the same warp. Here you can see one example. If these two threads, thread 0 and thread 1, need to update two different elements in different banks, for example, of the shared memory, that's perfectly fine. They can update these values. They can perform the read, modify, write operation in parallel with a certain latency. However, if these two need to update the same element in the same bank, we will have an serialization, we will have a longer latency due to the atomic conflict. Atomic operations are pretty useful for computation where the atomics are directly used on elements of an array that will be the output of the kernel, and examples of these are, for example, the histogram calculation or a parallel reduction. We will see examples of them in later lectures. And atomic operations can also be used for synchronization when the atomic operations on memory locations that are used for synchronization or coordination. For example, when we use atomic operations to update counters, to implement logs, to set flags, and so on. Atomic operations, as I said before, are useful to prevent data races, but they have the drawback of causing serialization, as I explained. We are going to talk in much more detail about atomic operations in a later lecture, in particular when we talk about histograms that are widely used primitive in image processing and other fields as well. As you may know, a histogram essentially counts the number of occurrences of a certain value in some certain input. For example, an image histogram will give us the number of pixels that have a certain pixel value. Problem with creating histograms on a GPU, calculating histograms on a GPU, is that we have multiple threads running in parallel, and these threads will have to update one single histogram that represents the whole input image. And what may happen here is that threads that execute together, like for example, the thread 0 and thread 2, have to update the same bin of the histogram. In that case, we will have an atomic conflict, serialization, and a little bit of loss in performance. But we will see ways of optimizing this histogram calculation as well. And same for the parallel reduction. I'm not going to talk in detail anymore about parallel reduction here, but atomic operations are also, or can be pretty useful to implement parallel reduction, and even surprisingly, or could be surprisingly efficient parallel reduction, as we will see. And finally, in order to finish this lecture, this introduction to the important performance considerations in GPU computing, I mentioned in the beginning that one of the key bottlenecks in GPU computing is that we need to move data from the main memory of the CPU to the global memory of the GPU. And after the computation has been done on the GPU, we'll have to move the results from the GPU memory to the CPU memory. And this is a cost that we definitely have to pay, but there are ways of alleviating this cost. And the way of alleviating this cost, or one way of alleviating this cost, is overlapping the data transfers with the computation on the GPU. And there is a way of doing that in the CUDA programming model, is the use of asynchronous transfers and CUDA streams. This is not only a CUDA feature, it also exists in OpenCL, where instead of being called streams, they are called common queues. But in both cases, either a stream or a common queue is defined as a sequence of operations that are performed in order. When we talk about operations, we might mean data transfers between CPU and GPU, we might mean kernel execution, or we might mean data transfers between GPU and CPU. Let's take a look at how to use these streams and asynchronous transfers in order to perform the overlap. What we are going to do is dividing the transfers and the computation into a certain number of streams. Let's assume that our number of streams is 4. What we have in principle is a number of input data instances. Imagine that we have a very large array and we divide this array into streams for example, pieces, parts, right? And also we can divide the total number of thread flocks that we would need to operate on these data instances. So if we are using 4 streams, for each stream, we are going to compute on D data instances, and we are going to use B thread blocks. So what that means is that instead of having to transfer the whole input data, and once the data is already completely in global memory of the GPU, we start the execution of the kernel. What we can do is dividing, in this case, the whole amount of data and all the thread blocks that we need to compute here, divide them into 4 pieces, and right after having transferred the first part of the data, we can start the execution on the GPU. We can start this partial DPU kernel that is going to use V/4 thread blocks, and at the same time, we can perform the copy of the next amount of data, of the next part of the input array. And after this one is done, we can compute on that part there. And as you see, we are overlapping the data transfer and the computation, and we are saving a significant amount of time. Actually, we can even estimate what's going to be the final execution time when we are using a certain number of streams. Here you see a couple of raw estimates that will give you an idea of what's going to be the overall execution time in case that we have a dominant kernel, which means that the execution time of the kernel is greater or equal than the data transfer time, or when we have dominant transfers, where the transfer time is higher than the execution time of the kernel. In one case, we will have the kernel hiding most of the data transfers, while in the other case, we'll have the data transfers hiding most of the execution of the kernel. And here you can see some sample codes of how to do this. If you really want to have a good reference, just go to the CUDA programming guide. But as you see, streams need to be created before using them. Then we can launch the asynchronous transfers, in this case using CUDA and copy async. Notice that one of the parameters of this CUDA and copy async is the stream number. Then we launch the corresponding kernels in each of the streams. Observe as well that the execution configuration, which is the number of thread blocks and the number of threads, now is accompanied by the stream number as well. And then here we have the asynchronous transfers for the results from the device to the host, from the GPU memory to the CPU memory. We eventually may want to synchronize when we want to make sure that all these operations that now are all of them asynchronous, if we want to make sure that they are finished in the host code, we'll have to use this explicit synchronization. And eventually, after we are done with the with all our streams and we don't need to use them anymore, we'll have to destroy them. Streams and the asynchronous transfers are extremely useful, as I said, to hide this long latency of transfers between the CPU memory and the GPU memory. And this can be applicable to many different use cases. Here you have a simplified example of video processing. In a non-stream execution, we would need to transfer the whole video or the whole sequence of a video to the GPU memory, and only after that start the computation on these frames by the thread blocks, whatever number of thread blocks that we need to use in this kernel. With the stream execution, we can partition the video sequence into different chunks. We can transfer the chunks. As soon as one chunk is in the GPU memory, we can compute on it, and at the same time transfer the subsequent frames. And this way save a lot of time thanks to the use of streams. Here you can see some performance results. This is execution time for different number of streams, in this case from 2 to 64, and this is a 256 bin histogram calculation of the frames of a video, and the size of the frames is, I mean, we are using 3 different frame sizes, as you see. We are comparing here the non-stream execution, that is the blue line, with the stream execution, that is the orange line. And we also represent here one performance model that we came up with. You can see how well or pretty well this performance model adapts to the execution time of the stream execution. And you can see what large performance improvements we could achieve. This is on quite old GPUs, GTX 2080 or GTX 4080, but as you see, 44% or 21% performance improvement, including kernel execution and including data transfers, of course, that we could achieve by using the optimal number of streams. And here you can see another example. This is RGB to grayscale conversion, also for frames of a video, and as you see, performance improvements of up to 63 in one case and 18% in another case. So these have been our performance considerations. Remember that main bottlenecks for GPU execution are the transfers between CPU and GPU memory, the accesses to the global memory of the GPU, because these memory access, we have to try to hide the long latency of this memory access. For that, we need large enough occupancy. We need to have enough number of active warps. We have to be careful, or should try to have memory coalescing, coalesced memory accesses, because this is a way of maximizing the memory bandwidth. And this happens when threads of the same warp access neighboring memory locations or memory locations that belong to the same DRAM bars. We should also take advantage of data reuse whenever is possible. And we have seen examples of how to use this, take advantage of this reuse in shared memory. This could also be possible in register file, as we will see in later lectures, but using shared memory might also be, we also have to be careful when using shared memory and avoid bank conflicts in the shared memory. Inside the SIMD lanes, inside the SIMD functional units, it's important to try to maximize the utilization of these SIMD units, maximize the utilization of the warps by avoiding the divergence. We will see good examples in later lectures, like the parallel reduction. And other considerations, we have briefly talked and introduced the atomic operations that may cause serialization, but they are very useful and really necessary to use in some important primitives. We will soon talk about the histogram calculation, and we will see ways of how to optimize the use of atomic operations as well. And finally, we have introduced the asynchronous transfers, CUDA streams, as a way of overlapping communication and computation in the GPU. So this is all for today. If you want to learn more about these topics that we covered today, I can recommend you chapters 5 and chapter 18, especially this last one, section 18.5, that introduces CUDA streams and asynchronous transfers, chapters from the Programming Massively Parallel Processors book. This is all for today. Please ping me if you need to answer any questions related to today's lecture. I'd be glad to do so, and I hope to see you in the next lecture of our course on heterogeneous systems. Have a nice day.